What up, ladies and gentlemen? We are taking a look at Unit 3 Postlab, and you look at this list and you realize it's really long, so this is going to be a little bit of a longer video, but if we could get this stuff down, you will see that this unit is really kind of wrapped up except for like one new concept. So knock these things out now. We will get some practice on it on a worksheet in class, and then we're basically done with Unit 3, which is kind of crazy to even think about. So, key ideas, you can write these things down. I would if I were you, and just kind of check them off as we go, and I will revisit these as we do it. So, in class, you will realize that we need to look at what does the slope represent in each graph. So, let me zoom out real quick, move on over here. We have the x versus t graph, and you notice that this is not a straight line. It was a curved graph, so what we had to do was we had to modify it, and we had to take t and square it. So you get t squared. Keep in mind when you square a variable, the units also get squared. So when I look at the meaning of the slope, first off, I think about the units of the slope. So I guess that should be slope units. And what I would say there is I'm going to say my slope units are going to be a meter per second squared. And when I think about that, I ask, what is that? Well, a lot of people said velocity, and well, that's not velocity because a velocity would be meters per second. Keep in mind this is an x versus t squared graph, so this slope is not velocity. So right now we actually don't know at the moment what that unit is. It's something we've never seen before. Maybe we might be able to come back to it and get a better understanding. Y-intercept is easy though. We take a look at the y-intercept and you notice that, well, it is when t squared is equal to 0. What is x? So in this case, x is going to be our initial position. So that would make a lot more sense to us, being that this is just representing the initial position that your cart started with. Hey, guess what? That should probably be about 0.0 or 0.15 meters, being that that's about how far you should have started away from the motion sensor. So, meaning and slope of that graph is pretty easy. Now, moving to the v versus t graph, meaning of slope. First off, like I said, I like to look at the slope units. In this case, the slope units is a meter per second divided by seconds. Now, whenever you're looking at something like this, dividing by a fraction or a fraction inside a fraction, I always say let's just simplify it and get a nice just standard fraction. So whenever I see this, I see a numerator and I see a denominator down here. What I'm going to do is I'm going to take the numerator, and when I divide by a fraction, I'm multiplying by the reciprocal, so my numerator stays put. I have meters per second, but I'm going to be multiplying by the reciprocal, which is 1 over seconds. And you notice the same unit comes out of here, meters per second squared. So right now, if I'm a good physics student, I've made a connection. Say, are these the same? And we're going to keep that on the back of our brains for a moment, but those might be the same. We're going to think about that later. However, you also note that this is a meter per second, which is kind of like talking about your change in velocity. And so I should probably be a little bit more specific. It is the rate of change in velocity. So we have a word for this. This is called acceleration. So what we can come up with is the slope of this graph is equal to what we have is acceleration, and it can be written short name as an A. And our units, the units can be written two different ways. The first way is a meter per second per second. The way I like to think about this is a change in velocity per a change in time. Or, if you wanted to, the unit that will work as well is a meter per second squared. That will also check out as So both of those work out just fine and dandy. Y-intercept, if we go on over here, you'll notice that the y-intercept is when t is equal to 0. The velocity is, well, this is referring to what we will call the initial velocity. We can represent that as a v naught as being the velocity at sub-0. And guess what? Your velocity should have been 0 because the cart started out at rest. Whew. So going on over here, slope and y-intercept for the x versus t graph and the v versus t graph, check. We got this new term called acceleration. We need to be able to use that effectively and know really what it means. And we're going to see y-intercepts, got that done too, halfway through the list. Good. Recap of old information. Alright, so old stuff from last unit. So, looking at this stuff right here, you can see that I can take an x versus t graph, and if you remember correctly, if I take the slope of this red line, that red line is representing the average velocity because it's delta x over delta t. You just take your two endpoints, draw a line, that creates the slope. That is representing the average velocity. So in our new Unit 3 with a curved graph, I can do the same thing. I can take my red line and I can say, okay, start here, connect these two, and I can say the average velocity is equal to the slope here. And now what it is delta x over delta t. That will work. However, we still haven't come up with a way of telling the velocity at some time. Let's call this some time t. What happens if I wanted to know what is the velocity at t? And, well, what I can do is I can say, well, this line between these 2 points is actually getting a closer approximation. But what we can do is we can start to shorten that line and put maybe these two together, and you'll start to realize as I continue to bring this time frame closer and closer and closer, that all of a sudden I can represent the velocity at this time t by drawing in a line that looks something like that. So you will note that what I've just drawn here is what we call the tangent line, and that represents the velocity, the instantaneous velocity. So let me actually write that down here. The instantaneous velocity. So this is the velocity at that instant t. And if you do not remember what a tangent line is, let me just kind of draw this in. If we have a circle and I said draw a tangent to that point right there, all what I would do is I would draw a tangent. Remember, it is only going to hit that circle at one single point. So new idea, the tangent line of the x versus t graph is representing the instantaneous velocity. So if I wanted to know the velocity right there, again, a very easy way, just draw on the tangent line, take the slope of that line, and guess what? That is going to be my velocity at that instant. So that's one new idea. The other, or I'm sorry, an old idea now into a new idea. The other one is the area of the v versus t graph. So remember that was equal to the displacement. Well, guess what? We can do the same thing here. We can say t here. We can take this area, and that area still represents delta x. Now things get a little bit trickier when we start thinking about negative areas in this case. So if I had a new v versus t graph and I drew my graph in like this, the question is, what area do I shade? And the area that I always shade is going from the line towards the t-axis. So in this case, here's my t-axis, here's the line. The area is going to be represented that piece right there. So again, those are just representing the delta x, exactly like last unit. So moving up, taking a look at what we have, recap of old information, slope of the x versus t graph. Remember that is the instantaneous velocity. Area of the v versus t graph, that is going to be still delta x. And finally, new information, we got this thing called an a versus t graph. So we introduced this idea of acceleration. So remember, the slope of this v versus t graph is acceleration. And now what we're going to do is we're going to have to create an acceleration versus time graph. So as I move on over here, we'll take a quick look. An a versus t graph, again, has positive and negative accelerations. Those just represent, again, the direction of acceleration. So this is telling me I have positive direction of acceleration, negative direction of acceleration. And in order to actually take a look at the slope, what I would do here is, as we did before, I would say, okay, my velocity has a positive slope. It is also a constant slope. So positive constant, remember the slope is acceleration, so I would say it's positive constant acceleration. So on over here, for that time period t, I'm going to want to represent a positive constant acceleration. So again, you will see constant acceleration means the acceleration is not changing. It is positive, as we can see by our direction, and that is represented like so. So that's a new idea, a versus t graph, that should be very easy to create. And last but not least, oh man, motion map with acceleration arrows. So I see this this word that I've used before, a vector. Keep in mind, a vector shows the amount and direction of your variable. So I would write that in, and I would say, okay, that is what a vector, it's showing the amount and direction. So if I had an object that started out t equals 0, at rest, so this is going to be the car going down the ramp, this object is at rest. So should I have a velocity vector on that one? No. However, right after it was released, the car started going down the ramp. So my next time interval, I'm just a little bit further away because it started to go down the ramp. So that's going to be there. Now, do I have a velocity at this time? Yes, I do. And I would represent it by drawing a velocity vector on there. A little bit further down the road, I am starting to cruise. I'm going to be at a further position away because I'm speeding up. And then my velocity vector is also going to get larger. And you're going to see, as I continue on, I'm going to be even at a further position away. And sure enough, my velocity has increased, so I'm getting a larger and larger velocity. So this would be exactly like the lab situation. Something that started at rest and got faster and faster and faster. And I just want you to note, real quick, I'm going to draw this in, but I'm going to erase it in just 1 second. The delta x's, the position changes, kept getting larger and larger and larger. And the reason being is we're speeding up, so the position's getting larger and larger and larger. That's why we had a curved x versus t graph. So that is represented in our motion map like so. The other thing now that we're going to have to do, and I'm going to do this in blue, is I'm going to draw in the acceleration, showing, again, acceleration is the direction and value of the change in velocity. Remember, we were talking about a change in velocity. So I'd ask myself, what is my change in velocity from here to here? And you're going to notice that it's a value, and then I would have to ask myself, what direction is that change? Well, I started with 0 velocity, and I gained velocity in that direction. So you notice that I started with 0 velocity, I had an acceleration, which gave me a change or a velocity now in the next second of that arrow. And I would represent this again. I would say, okay, I had this velocity, I have a change in velocity, which is acceleration of this, which now gave me a longer arrow. from here, again, I had this velocity, I had a change in velocity, which now gave me this arrow on over here. So the way that I like to think about it is, I'm going to just draw this out. I started at t equals 0 with no velocity, which is represented by the dot. My acceleration, which I think about as a change in velocity, is going to be that blue line. And my next time interval, right, the next time, which is going to be what I'm going to call t equals 1, is going to be those two added together. So that would represent t equals 1. And I can continue to do this. T equals 1, my acceleration is still going to be like that. So guess what? At t equals 2, I should have a velocity of both of these things added up together. This vector plus this vector, which gives me a longer vector going to the right. And you'll start to notice that is exactly what I drew when I drew my velocity vectors going to the right. We will take a deeper look into this tomorrow as we start playing with different situations. So, long video, my apologies, but you'll see we took care of the new ideas here, A versus T graph, and how acceleration is shown on a motion map. You'll notice the showing on a motion map is going to be really helpful. Thank you for listening. Bring all and every question that you might have thought about on here. We will definitely have a great discussion about this tomorrow. Have a great day.